Okay, we're going to continue with properties of the dot product and cross product. By the way, today is still Thursday, June 4, 2020. So we continue with properties. So associative property of the dot product doesn't even make sense. Asking the question of whether the cross product makes sense is a good question. We could ask that because the product does make sense. If you have two vectors, u and v, and cross them, you get a vector, and consequently, we can cross that again with a third vector w. And if we maintain the order of the vectors, then we can reassociate them. We can do u cross v cross w. And we can ask, are they equal or not? Question mark. And the answer is no. In general, they're not equal. So whenever we ask this question, when we ask equality, we mean, are they, and by they I mean the two sides of the proposed equation, are they always equal? So the key is to remember that when we are asking the question of whether two sides of an equation are equal to two sides of a possible identity are equal, we mean always. So if we can come up with a counterexample, then we can say, no, they're not equal. All it takes is one counterexample. And I can provide you with at least one. I'm not going to perform the computations because I think it is a good idea for the viewer to practice the cross product. Try multiplying something easy, 1, 0, 0, by 0, 1, 0. And then once you have that, multiply by just a generic ABC, ABC, cross product. And then multiply 0, 1, 0 with ABC. After you multiply those, then multiply 1, 0, 0 with the product, the cross product of those two. And you will realize that the two are not equal. Even that, yeah, we have to be careful because that doesn't necessarily count as a counterexample. In my opinion, I believe a counterexample should be even more concrete. So forgive me for doing this, but use 1, 2, and 3. That will suffice, just simple numbers. 1, 2, and 3 instead of ABC. Now we do have a concrete counterexample. When we perform those operations, we will realize that the final answer of that product will not be equal to the final answer of that product, unless I'm wrong. No, I'm pretty sure they're not going to be equal. I think. No. I am sure they're not going to be equal. Anyway, it is always good for a student in particular to be what I would call skeptical, reasonably skeptical. And by that, what I mean is, I believe you, but let me double check. I think I encourage students to tell me that, to think that, to be just a little bit skeptical and check on your own. Yeah. So we have commutativity for the dot product, skew commutativity for the cross product. Associativity doesn't even make sense for the dot product. Associativity doesn't work for the cross product. So these are kind of weird operations, if we can call them that, because they don't have the same kind of properties as other operations, such as addition of real numbers, multiplication of real numbers. Let's talk more about properties of the dot product and the cross product. So more properties. We have, for instance, if you dot a vector with itself, then you end up with two vectors that are parallel. You have two vectors that are parallel. We allow a vector to be compared to itself. Just in math in general, we allow things to be compared to themselves. So V is parallel to itself in mathematics. And this turns out to be the magnitude of V squared. Yeah. So that is handy. We can exchange the dot product with the magnitude, and sometimes the magnitude with the dot product when we square it. And this is always going to be positive as well as that. So we could take the square root on both sides. So, or another way to say it is that the magnitude of the can be thought of as the square root, the positive square root, which is this, what we mean, of V dotted with V. Let's switch back to cross product. I'm not gonna, well, if we cross V with itself, we're invariably gonna get 0, 0, 0, no matter what V is. Yeah. Regardless of the vector V. Yeah. So whatever V is, you're always going to end up with 0, 0, 0. Yep. And if you actually do, it is not a bad idea to actually do the experiment with a vector. So I suggest that to do, say 2, 3, 5, and cross it with 2, 3, 5. So you can verify my statement. I'm making a statement, and it is a good idea to verify it. That is not necessarily a proof, but to verify that I'm not off. Another property of the cross product is that the result of the cross product will be perpendicular to the first two vectors. Let me show you this. So this is a fact. Oftentimes we call that a theorem because it has been proven. So let me draw a picture very quickly. If you have two vectors, V and W, and you cross them, you're going to end up with a third vector, which is going to be perfectly perpendicular. So this vector is perpendicular to those two. Yeah, to those two. So this is going to be V cross W. It doesn't, this picture could be misleading because somebody may think, wait a minute, isn't that 90 degrees? So this is the sort of the X and the Y, and this is the axis. Not necessarily. Even if the two vectors are very narrow, if the angle between the two vectors is very narrow, so there is V and W, when we cross them, we're going to end up with a third vector that is perfectly perpendicular to the two, regardless of the angle between the two. Well, except if the angle is 0 or 180 degrees, then this gets reduced to nothing, to 0. But if the angle is not 0 or 180 degrees, 0 or pi, then we're going to end up with a non-zero vector that is perpendicular to the other two. Now, since we're allowing 0, 0, 0 to be perpendicular to any vector, we still end up with something that is perpendicular. It is just a trivial vector. 0, 0, 0 is what we would call a trivial perpendicular vector, because it is always perpendicular no matter what to any other vector. So that is a property, that is a fact or a theorem. Anytime you do a cross product, you end up with something that invariably will be perpendicular to the two given vectors. Yeah, one more. If the angle between the two of them is very obtuse, not 180 degrees, so if this is V, and actually let me change this. If this is W and this is V, and we do V cross W, then we will end up with this vector pointing down instead of pointing up. Yeah. So the order in which we perform the cross product operation is relevant. If V approaches W, then we use what is called the right-hand rule. That's it, right-hand rule, or the righty-tighty, lefty-loosey rule. So, you know, when you turn a regular screw, for instance, in one direction, the screw goes away from you. If you are facing the screw, it goes away from you, and that's what's going on here. By crossing V with W, we are thinking we're going this way, and that causes the vector to go in that, the resultant cross product to go in that direction. So down here, we go the other way. If we look at it from the top, instead of going counterclockwise, we're going clockwise. And so the vector, the resultant product from of V cross W will be going down instead of up, according to these pictures. That is a convention, just like the positive numbers go to the right, the negative numbers go to the left. It is a convention. We could have come up with a formula so it goes the other way. I don't really think there's harm done to go the other way. We could have started out the other way, and you know, with the cross product going the other way. And I think everything would have been okay, but I think, I'm guessing that everything would have been okay. But let's move on with properties. This is the cross product. Yeah, but there's more properties. The dot product is distributive. If we multiply by 0, you end up with 0. Those are properties you can review on your own. There's many sources to review some basic properties. Multiplying by a scalar is okay. There's no. Let me speak about that for a moment. If we have the dot product of two vectors and you're multiplying with a scalar, you can multiply the scalar with the first vector and then apply the dot product of those two, or you can multiply the scalar with the second vector and then do the, so this is what I'm trying to say. There's no big drama as long as we keep the scalar as a single scalar. So don't distribute the scalar. That's what I'm trying to say here. Use it once, whether it is after the dot product or on one of the two vectors before the dot product, but use it only once and you will be okay. So CV times, so what I mean by that is this, dot product of those two, or V dotted with CW. Yeah. So as long as we apply the scalar product once, we are good. The same thing happens with the cross product. So if we have C multiplied with V cross W, so there are some similarities and some things that are very, very different as far as talking about the dot product versus the cross product. So again, do not distribute the C because you're going to end up with a C squared. So just use the C once, CV cross W. So by that we mean that. Or V crossed CW. So if we multiply by a scalar, multiply it once and we are set. Distributive properties with addition work the way you would expect them to work. Multiplying by 0 gives you 0. Yeah. So those are, again, properties, simple properties you can review on your own. In geometry, geometrically speaking, there are two important facts or theorems about the dot and cross product. So these are geometric theorems. Yeah. Geometric theorems. The dot product of two vectors is the magnitude of V of one of the vectors times the magnitude of the second vector times the cosine of the angle in between them. So theta is the angle between them. Before I show a picture, I want to give you the analogous theorem for the cross product. So that's why we have theorems, two of them. So the magnitude of V cross W is the magnitude of V times the magnitude of W times the sine of theta. Okay, now there is a difference between those two thetas. Those are not necessarily the same theta. So we have to be careful with this. They're the same theta if the theta is acute, but if the theta is not acute, then that is not necessarily true. Let's see what the difference is. Well, let's talk about two lines. So when we cross two lines, not at a 90-degree angle, there are two possibilities for angles. So this could be an angle. We produce two different kinds of angles. This one and obtuse one, an acute angle and an obtuse angle. This theta is always going to be the acute of the two. It is going to be the sine in turn is going to be the same regardless. But if you're trying to find, if you do the arc sine to find the angle, if you're trying to find the angle, you're always going to get this one. So you got to be careful about that. With the cosine, it doesn't matter. See, the thing with vectors is that we have directions. Assuming this is the origin, we got a direction. Yeah, that was more of a 90-degree angle. Let me give you a different example. Yeah. So if you have two vectors coming off the origin, yeah, this angle is going to be the same in the two formulas. If the two vectors are sort of opposing each other in the sense that the angle between the two of them is more than 90 degrees. If you attempt to find the theta by applying the arc sine, you're going to end up with an angle that is less than 90 degrees. So you're not going to get this angle, you're going to get the supplement of this angle. So you got to watch out. It is a matter of basic trigonometry, but you got to be aware, if you apply the arc sine, you may not end up with the correct angle. The arc cosine will always give you the correct angle no matter what. I mean, as long as we are within 180 degrees, which will always be the case in this context. So just be aware of those two. So one gives you the cosine, one has to do with the cosine, one has to do with the sine. And again, this causes the dot product and the cross product to be valuable because they can detect perpendicular vectors, parallel vectors, and not only that, they can actually tell us more about how far off from being perpendicular or parallel they are, which is very important in physics. Another quick fact. Well, we already established this in part one of the videos of dot product and cross product. I'm going to repeat it one quick time. V times W is equal to 0. If and only if V is perpendicular to W. We are assuming that the zero vector is perpendicular to all the vectors. And so this is a fact, or facts. That's one of them. V cross W is equal to 0 if and only if V is parallel to W. Can we combine the dot product with the cross product? And the answer is yes, indeed we can. There is what is called the scalar triple product. Of three vectors, hence triple. And there are two forms of it. If you have three vectors, u, v, and w, if we dot u with v cross w, that is always going to be equal to u cross v dotted with w. And the result of this is what is called the scalar triple product of u, v, and w. Yep. Yep. If we form the geometry of this is that if you have three vectors, not necessarily lined up with the x or y axis, just three vectors. So we have a vector, another vector, u and v. We can form a parallelogram by copying u and adding it here, and copying v, adding it there. And then if we have a third vector, w, then we can copy that vector there in each one of those corners. And then we can form what is called a parallelepiped. Let me write it down because that is not so easy to pronounce. Parallelepiped. There you go. And the magnitude of this triple product will be equal to the volume of that. Yep. Yep. So that is a combination, and a nice combination and application of the cross product along with the dot product. This has to do with the sines and the cosines resulting of the cross products and the dot product. So the angles formed gives us the altitudes of the parallelogram and then the altitude of the parallel piped. And that's how we obtain the volume, because essentially what we have to do is multiply the magnitude of U times the altitude of this parallelogram, which has to do with the cosine, and that's how the cross product gets involved. And then we multiply it with the sine to obtain the height of the parallel pipe, and essentially that's how we obtain the volume. Please practice this to obtain volumes. This can also tell you whether those 4 points, so mind, we have 3 vectors, but we have 4 points in play here. We have the origin, U, V, and W. So if we wanted to use, let me make a point of this. Let me take the time of doing this. If you want to know whether 4 vectors, okay, so to know whether 4 vectors, and by that we mean points, are coplanar. See, three points are always coplanar in space, but 4 may or may not be coplanar. Just like 2 vectors are collinear, 3 vectors are always coplanar. They're on the same plane. There's a plane that contains the 3 of them. That's what I'm trying to say. But 4 vectors may or may not be coplanar. So to know whether 4 vectors, and by vectors we mean points, are coplanar or not. So let's say you got 4 random vectors. Now this is a 3-dimensional space, so they're on this page, but they're actually, this one could be closer to us, or this one could be farther away from us, and we don't know. They're not necessarily in the same plane. What we want to do is anchor all of these points so that one of them becomes the origin. So let's say the origin is here. Then with this origin, now we have 5 points. 1, 2, 3, 4. Let's call them capital A, B, C, D. Yep. So when we think of this point, we're thinking, well, from here to here. When we write the coordinates of this point, we're thinking, so we're talking about those vectors. But we really want to move this back, or we want to move the origin, which is the same thing as moving D down to here. We want to move this back to the origin. So instead of having 5, we have then 4. Yeah, because implicitly, when you have 4 points, we really have 5 because of the origin. To avoid that, we move all of them. So what do we do? So change all of that system into a new system. A minus D, B minus D, D minus D, and so yeah, that could be here. So now that becomes the origin because D minus D is 0, the 0 vector. And then you have C minus D, and then the other one over there and over there. And then we can apply the scalar triple product to those 3 vectors. If you end up with 0, then the 4 points were coplanar to start with. Yeah. If you end up with a number that is different than 0, then the 4 points are not coplanar. This is a rigid motion, we're shifting everything so that D becomes the new origin. And by the way, it doesn't have to be D, it can be any of them. You can move things so that C becomes the new origin, or B or A, it doesn't matter. The key is to transfer things so that one of them becomes the origin. This is a very important part of this application. Let's talk about torque. For torque, we use the lowercase Greek tau. That's the name of the letter. And again, it's a lowercase. It's not an uppercase tau. And torque measures a rotational force. So that has to do with rotational force. Yep. And the way we figure the torque, by the way, the torque represents rotational force, and it is a vector, as a vector. Yeah. So if we have a lever, so this is a pivoting point, a lever, and we apply a force as a vector, yeah, this is coming towards us. If we push this way by the right hand rule, or the righty-tighty, lefty-loosey, we are turning, pretend our hand is behind, and we are turning this way, and that's the way I would turn if I was screwing something in. So by turning that way, we're screwing towards the camera. This is going towards the camera. So the resultant vector is going, so the tau vector is going up. Yeah, so we think of this vector this way. Yeah, the lever is going in that direction. We think of this lever as a vector going in that direction. And if this is 90 degrees, then there's not much to it. All what we do is just multiply the magnitudes of the vectors to obtain the magnitude of the torque. So the torque is coming towards us. Towards us, or the camera. Yep, yep. And yeah, if we, on the other hand, I'm pausing for a moment because I want to make sure that the multiplication of the vectors is correct. Let's say this is u, the vector u, and this is the force. We got to multiply u cross f to get this direction. Yep. Let me pause this for a moment. All right, I'm back. The only reason why I paused is because I wanted to make sure my directions were correct, and they are indeed correct. Yes, the directions of the vectors are correct. The units of torque, it depends. In metric, there would be Newton for force and meter for the magnitude of this would be in meters, and the magnitude of the force would be in newtons. So the units would be newtons meters. So newtons and meters. If we use English units, then we have foot pounds, yep, or pound foot, yeah, foot pounds. Yes, so the force would be in feet, rather in pounds, and then the length of the lever would be in feet. The picture could be a little misleading because the length of this vector has to do with a force, which we don't necessarily, you know, you can have a lot of force in a small body or small force in a large body. So physically, this represents the mass of the force, or another, if we were talking about a weight that applies force by gravity, then that would be the case. But what I'm trying to say is this only represents force. The units of those two vectors are different. This is force, while this is a distance, a length. And that's how we measure torque. If the angle is not 90 degrees and you want to know the magnitude of the torque, then multiply the length of the lever, multiply it by the magnitude of the force, and then multiply by the sine of the angle instead of multiplying just by 1. We end up with 1 if the angle is 90 degrees. Of course, the sine of 90 degrees is 1, but if the angle is off, then figure out the sine of that angle, and that's going to give you the correct proportion of the force that is used. And you may ask, well, what is when we have a lever and you apply a force, which angle are we talking about, this one or this one? And the answer is it doesn't matter, because the sine of one is the same as the sine of the other. So it doesn't matter which way you do it. Typically, I guess we're using the inside, but what if we had a force being applied outside? Then we still end up with the same thing. It doesn't matter. Oh, that is interesting. So if you go off the 90 degrees, if you go and start pushing in this direction, and you go the other way and push in this direction, you end up with the same kind of torque, as long as the angles is the same going off the 90-degree angle one way versus the other. You lose torque. And if you push in this direction, then you're not applying rotational force anymore. So this is a neat application. Torque is a neat application. There's many, many more geometrical applications of the cross product. We're going to milk the cross product quite a bit. There's many applications of the geometric applications of the dot product too. Let's talk about projections. We can project one vector over another vector. So let's say you have a v vector and a w vector, and this is not necessarily lined up with the x-axis. It's some random vector anywhere in space. All right, so this is the origin, w vector. We can project this vector onto this one by drawing a 90-degree angle line, drawing an altitude where this is the base. And this length is the component, this distance is the component of this vector onto this vector. So this is the component of W on V. The shorthand for this, instead of writing component of W on V, we can just write COMP of W on V. So we draw V with a smaller font as a sub-index of COMP. Just like a logarithm, you put the the base of the logarithm as a subindex or an exponent. So this is the length of that, and there is a formula for it. It is VW in this case, so the dot product of the two, and then divide by the magnitude of V. That gives you the length. Yeah. The dot product is the cosine. Oh yeah, that's why we have this, because we have a right triangle here, and this length has to do with the cosine of that. I mean, we use this as the hypotenuse. So this length is the magnitude of W times the cosine. Okay, so let's derive Y. So initially, if we wanted to know this distance, and this is a right triangle, what you want to do is multiply, if this is theta, we multiply, so the magnitude, well, this distance, let's just call it answer for now. The answer for this length is magnitude of W, which is the hypotenuse of this triangle, times the cosine of the angle. But the cosine in turn is equal to the dot product of V with W divided by their corresponding magnitudes. And then we can simplify the W. So the W has to be different than 0, so we can simplify. So we can have any kind of projection. Otherwise, we have no projection. The projection is 0 automatically. If W is 0, then cancel those two out, simplify, and then we end up with VW over the magnitude of V, which is this answer. All right. Now, sometimes we do want to find this vector itself. And again, this vector is not necessarily lined up with the x-axis, is some vector in space. Yep. So if we want to find this vector itself, what we have to do is give this is a scalar. Again, a scalar divided by a scalar is a scalar. So it's a number, it's a length. And we want to know, we want to give this vector this length. So we have this direction of V. Yep. And by the way, that is the projection. This vector itself is called the projection of W on V. So we want the direction of V to start with. So that's the vector V. I'm going to emphasize that we have the vector V. That gives us this direction, but not the right length. So we're going to neutralize the length initially by multiplying by the scalar 1 over V, magnitude of V rather. So now this is a new vector. We have shortened this vector to a unit vector. Now the length of the vector is 1. This new vector has the same direction, exactly in the same way, but now it is a vector of length 1. If we multiply by this scalar, then we're going to stretch it out to the length we wanted it to be. So we multiply by, this is not dot product, this is just regular product. Well, actually, I lied. This is the scalar product. Scalar product with a vector. And this multiplication is going to be a real number multiplication. We're going to multiply V dotted with W over magnitude of V. Yeah. So boy, there's a lot of things going on here. This is real number product. So just the one you learned back in elementary school. And then this is dot product. Whoa, there's a lot of things going on. And this is why we need some of the basic properties. So if we're multiplying with a scalar and then another scalar, there's no issues arising from that. We can multiply those two first and then with the vector, and that's what we're gonna do. As we do that, oh, there's nothing that will simplify, so we just end up with VW. So let me rewrite this as V dotted with W, which is a scalar. Even though this is the dot product, the product itself, the answer to the product is going to be a scalar, so we can divide by the magnitude of V squared. And of course, those two are not going to cancel because there are terms involved. This product involves additions, and so does this. And so there's additions inside of the square root if you want to find the magnitude, but then we get a square. There's additions involved, and so we cannot simplify terms across fractions. So this doesn't simplify. And then we still multiply by the vector V. This is the same V all over. I'm just emphasizing that this is the vector V. And that's the formula for obtaining the vector that goes in exactly the same direction as V, but as a projection of W. What that does is that if you find this vector, then we can easily figure out how to get to this point by using a fraction of this vector. Let me give you an example. I came up with an example that I found interesting. Okay. We do this kind of problem in Calculus 1. Usually in the first semester of Calculus 1 by means of derivatives. We're going to do this problem geometrically. So this is a problem that we're going to solve. This is the x-axis and the y-axis. Consider the line y equals a third of x. And consider the point 4, 5. Somewhere in here is the point 4, 5. So a typical problem, an optimization problem in Calculus 1 is to find the point on this line that is closest to this point. And some students try to do this geometrically. Some students are successful. But of course, they did not use calculus. Now we're going to do it geometrically using the dot product. So on this line, we will have a point with coordinates, let's see, 3, 1. So if x is 3, then the y is 1. So this point has coordinates. There's a point there with coordinates 3, 1. So we can think of this as a vector. All right. Now, if I want to find the point on the line that is closest to this one, this distance has to be minimum, which means that if we think of this line, there's going to be a 90-degree angle between this new line joining the point with the line and the original line. Yep. So think of this as a vector, the vector 4, 5, being projected onto the vector 3, 1. So we want to find this point, which would be equivalent to finding the vector, okay, which is the projection of 4, 5 onto 3, 1. So notice that 3, 1 is shorter than 4, 5. The magnitude is square root of 10. The magnitude here is 25 plus 16. Yeah, it's way more than square root of 10. So this vector is way longer. And the projection is going to be out from 3, 1, but that doesn't matter. So we can either use the formula or we can sort of think this through. Yeah, let's use the formula. So this vector here, let's call it V. V is going to be the projection of the vector 4, 5, 4, 5 onto the vector 3, 1, 3, 1. I didn't give it names because the vectors are showing up, and we can do this. So let me dig out the formula that I just wrote down here. So multiply the two vectors. So this is equal to the dot product of 3, 1 dotted with 4, 5. Oops, nothing else. Divide by the vector we're projecting onto, which is 3, 1, the magnitude of 3, 1, and then multiply scalar multiplication with 3, 1 itself. So we have a scalar multiplication going on there. Okay, so 3 times 4 is 12, 1 times 5 is 5, 12 plus 5 is 17. Oh, I forgot a squared up here. So we got 17 on the numerator of this fraction. The magnitude of this vector, of course, is going to be 9 plus 1, 10. Square root of that is the magnitude, but then we're going to square that, so we end up with 10. Times the vector 3, 1. And that, of course, is 1.7. This is a nice decimal. It's a terminating decimal, so we can use decimals without sacrificing any accuracy. We don't have to use approximations. 3, 1, and that's going to be 5.1, 5.1, 1.7. There. So this vector up here has coordinates 5.1, 1.7. And that is precisely the vector, that is rather the number, the point, which is the same thing as a vector, the point that is closest to that one, because there's a 90-degree angle between this height and this line. And without using calculus, using geometry, and notice the computations are very, very straightforward. If you want to find, then once we have that, then we can actually compose 4, 5 by this vector plus this vector, so we can find what this vector is easily by subtracting this minus that. Yeah, it goes to the left, so that makes sense. We end up with a negative number. So this vector is, this one is the vector 4 minus 5.1, so negative 1.1. So it goes to the left and then up. 5 minus 1.7 is 3.3. Please double check my numbers. I just did this. Yeah. Yep. So now we have two vectors whose sum is 4, 5. But the neat thing about those vectors is that we can walk along the line y equals 1/3 with one of the vectors, and then get to the closest point where we can take off at a 90-degree angle and go in the other direction. I think this is a very neat problem to find the closest point to this 4, 5 along the line y equals 1/3 of x. Before we finished with this, there's one warning I have to tell you about. If your line does not go through the origin, then this is not as straightforward, but it has an easy remedy. So let's say you have a line, just a random line that does not go through the origin, and you want to find the point that is closest to this line, rather the point on the line that is closest to the given point by the same means. We cannot apply that process that we just finished to this example because we have to have the origin. When we think of these points, we're taking into account that they're coming off the origin. So this is not going to work as well, but it has an easy remedy. All you have to do is shift everything down, down here. So then it goes through the origin, which means that you have to shift this down, a rigid shift, find the point, and then shift back. And then you're all set. So you have to be careful when things are off the origin. And this finishes up my second part of the dot product and the cross product.